Hello everyone. Thanks for the introduction, Mr. Chair. My talk is about the advanced membrane materials for water treatment and, of course, the path for commercialization. University of Alberta, just an introduction, very exactly we are located. We are in Alberta, which is a province of Canada. It's famous because of its breathtaking natural beauty, and it's energy province. We have oil and gas, and it does have a strong economy because of the oil and gas industry, of course. And two modern cities of Alberta are Edmonton, that we are located in Edmonton, and Calgary. Where is the University of Alberta? Of course, it's in Alberta's capital city, which is Edmonton, and Edmonton has 1.5 million population. It's Canada's festival city. It does have clean and safe environment, and of course, diverse and multicultural characteristic, which is the characteristic of all cities in Canada, of course. And University of Alberta is always a top 5 university in Canada. We have 200 plus undergrad programs, 367 master and 172 PhD programs, and more than 40,000 students, and 18 faculties. And pretty much it's like RWTH Aachen in Germany. And because of that, we are a sister university. We have MOU agreement for collaboration. Advanced Water Research Lab is located in Mechanical Engineering Department at the U of A. And I'm the head of the Advanced Water Research Lab. Our mandate is to conduct pioneering research on the development of high performance materials and processes, mainly for water treatment. We just recently started gas separation also in my lab. There are currently 3 postdoctoral fellows, 9 PhD students, and 3 Master of Science students working in my lab, and 14 PhD and 15 MSc already graduated in my group. I have an easy job today because everyone here in today's event know about the membrane technology. Membrane is a semi-permeable barrier that allows the passage of desired material like water and prevents some materials to pass through, like contaminants. And based on the driving force, we are classifying membranes to concentration-driven, like forward osmosis, electrical-driven, like electrodialysis, temperature-driven, like membrane distillation that my colleague, Professor Gamaluddin, presented this morning talk, and pressure-driven, which is the focus of my talk today, is nanofiltration, reverse osmosis, microfiltration, and ultrafiltration. 90% of the membranes on the shelf in the market are made in spiral-bound modules configuration, and they are mainly thin film composite membranes. And in a spiral-bound configuration, membrane material itself, a feeder spacer, and a permeate carrier are wrapped around the perforated tube. And we can collect the permeate through the perforated tube in the center. So if you look at the membrane, the thin film composite membrane itself closely, and if it's the RO membrane or nanofiltration membrane, you can see that it does have 3 layers itself. The top layer is the active layer polyamide layer. The middle layer is a support layer, is a microporous or nanoporous MFUF membrane, microfiltration, ultrafiltration. And the bottom layer is a polyester fabric. So in AWRL, in my research group, we are making the middle layer and the top layer. And the middle layer is made, as you know, and you are doing a great job. My colleagues who are holding this conference, you're making PVDF spiral modules, and I'm really impressed. They are made by phase inversion method, and the most important phase inversion method is a non-solvent induced phase separation. And of course, we are making a casting solution. We cast the polymer on a suitable support, and then the phase separation happens, and we are making a porous membrane. And the porous membrane can be like this. You can see the cross-sectional image that it's a porous structure, and the pore size and the morphology of the cross-section and the top layer can be controlled by different parameters, like the viscosity of the casting solution, like the additives we are using, the temperature of the coagulation, and many parameters we can control the pore size and morphology. And the top layer is made by, of course, interfacial polymerization reaction between 2 monomers. Here we have MPD, which is M-phenylandiamine in water, and TMC, which is trimethyl chloride in organic solvent. Water and organic solvent are immiscible, and then the reaction happens between the MPD and TMC at the interface of the water and organic solvent, and we have a very thin layer of polyamide formed on top of the polysulfone or polyethersulfone MFUF membrane. And the thickness of the top layer, again, can be as low as 15 nanometer. And so you can see here the AWRM membrane casting machine that we have for the bench scale casting. We made this machine ourselves. So it's a generation 3. We also made generation 4 and 5. We send it to other university like University of Alabama. This is just for the, I can say for the research purposes, of course. It's not a larger scale fabrication. And we are making such devices for research purposes, and we are sending to other universities and research centers. You can see here we have a lignin-based membrane. The color is a wood color, and the additive is lignin here. And we are just pouring the solution, and then actually we are casting that, and then we are putting that in the water. The non-solvent induced phase separation happens. Here's a summary of research works in my group. We are fabricating advanced RO membranes, precious metal recovery using selective nanofiltration membrane, energy harvesting from wastewater by PRO, pressure retarded osmosis method, removal of emerging contaminants like PFAS from wastewater, as my colleague, Dr. Gamaluddin explained, fabrication of electroconductive, electroresponsive membrane. This is a research work that I'm doing with the RWTH Aachen as a part of my Humboldt fellowship. And fabrication of green membranes, like using lignin to make membranes, fabrication of electrospun nanofibrous membranes, like face mask filters, and energy management of water desalination by artificial intelligence, and designing next generation membranes by machine learning and deep learning methods. Today, I'm focusing on these two, fabrication of advanced RO membranes and precious metal recovery using selective nanofiltration membrane. And this is usually the path for commercialization that we consider. We start with a lab scale fabrication and characterization. And this is a TRL 1 to 3. And then we do the filtration test, and we file patents. This is TRL 4 we consider. After that, we validate and demonstrate the fabricated membrane at the TRL 5 and 6. And finally, we are going to TRL 7. After TRL 7, TRL 8 and 9 is really difficult. So this is not, I can say this is not the mission of the university. So I will explain it later. So I have two examples. First, fabrication of advanced reverse osmosis membrane and precious metal recovery using selective membranes. So this one is the fabrication of advanced thermally unstable TFC-RO membranes. In some industrial application, it's really needed to for our membranes to be stable at temperatures more than 45 degrees C. And you know that RO membranes in the market, they are not stable for a long time. So what exactly we did in this study, if I want to summarize, that we use another monomer for further cross-linking of the polyamide structure. Further cross-linking means higher thermal stability. So we usually use MPD and TMC for making RO membranes. So here we are using TAP. It does have 3-amine, and the name is 3-amine pyrimidine. And we will have more cross-linking of the polyamide structure, and definitely we are getting a stable flux at high temperature. For example, here you can see that when the temperature increases from 25 to 75 for the fabricated membrane with the high concentration of TAP, we are getting a high flux and it's stable. Now, if you look at the commercial membrane at 75 degrees C for this temperature range, for example, for FilmTech VW30, for Suez, which is now Veolia membrane, and for the Tricep X201, we have a flux decline over time. So if we can get a stable flux over time, that's a thermally stable membrane. So we could do that in the lab scale. Again, I emphasize in the lab scale. Another method to make advanced thermally stable membranes is to make thin film nanocomposite membranes. You can add nanoparticles like TiO2, graphene, nanodiamond, metal organic framework to make thin film nanocomposite membrane. The major challenges are aggregation of nanoparticles, of course, and we will not achieve a good dispersion and distribution of nanoparticles. Another major challenge is the compatibility of the nanoparticles with the polymer matrix. That's the biggest challenge, of course. So to improve the compatibility, of course, we can functionalize the nanoparticles. What exactly we did in this study for the nanodiamond, we functionalized the surface of nanodiamond with the same functional group that participate in the reaction in the interfacial polymerization reaction. You can see here we have MPD group on top of the nanoparticle. And so then we have the covalent bonding between the particle and the polymer matrix. So that helps actually for more compatibility of the nanoparticle in the structure. As you can see here, again, actually with the, we are comparing the Suez AG TFC 1 to TFN 400. For the TFN 400, and we are here, we are getting high flux and it becomes stable rapidly at high temperature, 75 degrees C. So again, NaCl rejection, you can see the TFN 400 that we have 400 ppm nanodiamond. We are getting high rejection of NaCl and of course high flux together. Again, this is the lab scale. There are a lot of challenges for making larger scale thermally stable membranes, and those membrane manufacturers usually are not willing to add nanoparticles to their structure. Another one is fabrication of advanced antibacterial RO membranes. So the idea was to use AG-MOF, metal organic framework, to top layer of the membrane to make it antibacterial. And you can see that we made the membrane, we got good results. And we found that this one, advanced antibacterial RO membrane, is closer to commercialization because those manufacturer, big membrane manufacturer like Veolia, like DuPont, they're willing to adapt this technology for making new types of membrane rather than using nanodiamond or other materials to make, because it's not expensive. The materials can be easily added to the interfacial polymerization reaction, and they don't need to change the manufacturing process. So we decided for this membrane to go for the higher TRL. And of course, we did some tests. We compared our results with the Veolia membrane. And then we noticed that, oh, this is worthy of patenting. So because we are getting good results, at the same time, the membrane is antibacterial. And this is what exactly those membrane manufacturers, they like. And so this is the patented membrane. So I can say that in this one, now we are in the TRL 7. After that, this is very difficult. So we have to talk to the membrane manufacturer, and then actually we have to out-license our technology to them for memory manufacturing. I can explain it later. Another example is lithium separation using, for example, nanoparticles. So for the lithium separation from brine, the major challenge is separation of lithium from divalent ions like magnesium and calcium. And for that, we have to make the membrane as positively charged as possible. For doing that, we should add some positive charge functional group to the membrane. It can be actually through the nanoparticles that they have positive charge. So here we have functionalized SiO2 nanoparticles, which are positively charged. We can either incorporate this silicon nanoparticle into polyamide layer, it participates in the reaction, or we just can do the surface coating. And in this case, we can make the membrane more positively charged. And you can see here, for example, in this graph that we can get the selectivity as high as 50 for such membranes. We did the test for some simulated brine with the high concentration of with the high TDS of the brine, like 5,000 here and 18,000 here TDS. With the concentration of lithium here is 60 ppm, here is 70 ppm. And the idea was the separation of magnesium from the lithium. So in this case, we can also see that these membranes are doing perfectly in the lab scale. But the challenge is the attachment of the nanoparticle on the surface. And that challenge actually causes the secondary waste, and those membrane manufacturers, they don't like it. They don't like the concept that those nanoparticles can be separated easily and the membrane can lose its properties over time. So we can see that it works in the lab scale. Of course, we can publish in good journals, but still the perspective for commercialization is not high. But with the same example, this one has a higher perspective for commercialization, that we are doing like, we are using chemicals for surface modification. Chemicals which are positively charged, and they can attach to the surface firmly, directly to the surface, like arginine. Arginine has a high, yeah.
Professor Sadrzadeh, you have 5 minutes more.
So how many times do you have? How much time?
2 minutes? 5 minutes more, sir.
Yeah, sure. 5 minutes. Yeah, it's more than what I want. Yeah, sure. And here, arginine, for example, here it does have NH2 functional group. NH2 in the water protonates to NH3 plus, and of course it becomes more positively charged. And you can see that we did some tests in the lab scale. We got actually the XPS results and everything to make sure that it is attached to the surface. And then actually we did some tests on the selectivity, and we could get a high selectivity, like the selectivity of the magnesium and lithium, like around 40. And then this one, we patented this one. So we could see that it's very good. And of course, the only commercial lithium selective membrane in the market is FilmTech Line XD element. And we compared our results with their results. We could get better results than them. And so we filed a patent. And then after that, we can go to the larger scale. After this, after we got the TRL5, now it's time to go from TRL5 to TRL7. As I said before, whatever we got so far was at the lab scale and bench scale. So if we want to compare our results with the real dopant and hydronautics and Veolia's membrane, we have to make at least such size membrane, 18, 12-inch modules. So we have the machine, of course, in our facility. We have cutting, folding, gluing, ruling, trimming, vacuum testing for the QA, quality assurance, QC, quality control. And the final product is 18, 12-inch module that you can see here. The idea is that we should make membranes at a scale that can be validated by relevant industries, as you're doing that yourself. And I could see your PVDF membranes. And this is one of those machine that is working. It's a cutting and folding device. And so we are just doing the cutting of the membrane through the spacer permeate carrier. And then actually at this stage, we are doing the gluing and ruling. As you can see, it's not still fully automatic, but we are going to that direction that we can make actually our membrane fully automatic. And then we have a rolling here. And then we have the covering, wrapping with the blue cover. So it's an 18, 12-inch module that we are making. Since the pressure is not high, we are going to maximum 300 PSI, that blue cover would be sufficient. If you are going actually to higher pressure for like seawater desalination, we have to have an FRP machine for the plexiglass wrapping that we have it, but we don't need that for RO membranes like this. It's a brackish water RO. And so the conclusion of my talk, specialty membranes that the feature thermal stability, antibacterial activity, and stimuli responsiveness, they open additional avenue for us as university professor for commercialization. If we make a membrane that is already in the market, like a phase inversion MFUF membrane or RO membrane, brackish water RO, this is really hard to compete with the established membrane manufacturer. The only thing that we can do is to give them the license for manufacturing the membrane at a larger scale. Otherwise, we cannot compete unless we have local industry as end users that they're ready to buy from us. Thank you very much. I would like to appreciate the time that's given to me for presenting my research. I would like to thank my students, postdoctoral fellows, and industry sponsors. I'm ready to take any questions.